Okay, so probability and binomial distribution again. So here's our probability distribution we're going to use for these types of questions. We're talking about success rates, so probability of success, probability of failure, number of success rates. This is essentially number of failure rates, okay? What we hadn't talked about before is our expected value. So the expected value is, say we were to run this trial over and over and over and over again, how many successes do we expect to have over the course of an infinite number of trials? Or in our case, our expected number of trials, whatever our n is. So whatever the number of trials is, we multiply it by the probability of success, and that's our expected outcome. Okay. So quickly go through this question. Suppose that 5% of the first batch of engines off a new production line have flaws. Okay. So what they're saying is they kind of have a failure rate. So your failure rate is 5% here. And an inspector randomly selects 6 engines for testing. Okay, so they've decided to choose 6 engines for testing. They want us to show the distribution. So in other words, we're going to set this up again. There's essentially, we're going to have to run through this formula here 6 different times. So I'll run through kind of the first and the last one, and we can kind of fill in the rest using intuition. But our formula, once again, states that probability is equal to combination of success, probability of successes, failures, Okay, so let's pull out our important information. So very first one, we're going to be working with when x is 0. So that's a probability that there are no failures in this case. Okay, so I know this seems a little counterintuitive, but our probability of success is actually their probability of flawed engines. Okay, so that's why I meant where you can technically make this p-value a failure rate. It doesn't matter. Just be aware of what it is you're trying to measure for. Okay, so what's the probability that none of them, of the 6 selected, will have flaws in them? Okay, so let's set it up. We're talking about when p is at 0. Okay, the number of tests, well, there's 6 trials, so we're going to have 6 combination number of, they usually call it successes, but in our case, it's actually failures. Okay, our x is going to be 0. The probability of having a failed engine was 0.05, so that's 5%. So you divide it by 100 to create a decimal there. Okay. Again, we're looking for having no flaws, so 0 success or failure rates, they would call it. The Q is the rest of our probability. So if it's a 5% probability of engines having flaws, that means there is a 95% probability of the engine not having a flaw. Okay? And then our power is just the number of trials subtracted by the number of successes, and that's 6 subtract 0 in our case, which essentially becomes the value of 6. Okay? So you would run this out and you would get some probability. And what we need to do is continue this many, many times. And what I'll do is I'll fill in the last one too, so you can just kind of see, but we would continue to fill this out. And then at 6, we'll fill it in one more time so you can kind of see the difference. There's still 6 trials. This time we're talking about 6 success rates, or in our case, all 6 of the engines being flawed. There's still a 5% chance of that. But our exponent in this case is going to be the number 6. Okay, so we're looking for all 6 of them to be flawed. The probability that we have no failures is still 95%, but this part is 6 subtract 6. So what we're talking about is we're going to have no good engines when the inspector takes it. So what's the probability that there are no good engines? So the difference between the first one and the last one is that in this one we're talking about having no flaws, so none of the engines are flawed. And in this one we're talking about all 6 of them being flawed. So this probability is going to be really, really small. Okay. So again, I did the rest of it all up on an Excel sheet so we can actually see the probability. So give me 1 second. Okay, so here's our Excel sheet. Again, this should be success trial, so that should be an X. So I put down here, this one's a little more detailed. Success rate or flawed engines is a 5% chance, and this is a failure to have a flawed engine. So really what it's saying is not having a flawed engine, which is a 95% chance rate. Okay, so I kind of ran the numbers through here. This is our combinations. That's wonderful. Probability of success, probabilities of failure. And this is what the probabilities came out to be. So what is this one saying? Remember, we multiply it by 100. It gives us roughly a 73% chance that out of all 6 trials, none of them will be flawed. Yeah, it makes sense because there's only really a 5% flawed rate. So if you take 6 engines, there's a pretty good chance none of them are going to have a flaw. Our second one says there's a 23% chance that one of the engines will be flawed that the inspector has chosen at random. Our third one here says there's a 3% chance that 2 of them would be flawed. So you can tell that it's already dropping quite a bit because the flaw rate is 5%. It's a really low rate. So the probability that we're talking about half of them being flawed is very unlikely. Okay, so in this one it's 0.2. And then let's just kind of focus on the last one there. Having all 6 of them to have flaws, even though there's only a 5% chance rate of that, the probability that the inspector chose 6 flawed engines is technically 0.00000015625. So like it's very, very unlikely that all 6 of the engines that the inspector chose would all have flaws in them. I summed them all together. It should add up to 1. Clearly Excel did some kind of rounding and it's just off by a very, very small decimal here. Okay, so all of them, they encompass all the possible probabilities here. We still got to figure out the expected rate, and that's actually much, much easier to calculate. We just look at the number of trials, and remember this one was 6, and the probability of, usually again they call it success, in our case it's a flawed engine. Okay, so to get the expected value is n times p. Well, there are 6 trials times the probability is 0.05. So the number of expected flawed engines here is 0.3. So you should have 0.3 flawed engines, which in reality doesn't make sense, right? We can't have 0.3 of a flawed engine. We either have a flawed engine or we don't have a flawed engine. But had we ran more trials, let's just for example say that in another case n was equal to 100. Okay, so if we had 100 times 0.05. Then the expected number of flawed engines, if we drew 100 of them at random, would be 5, which makes sense. That means we pulled 100 engines, we should expect about 5 of them to have flaws in them, and the rest of them to be completely fine.